So now floor systems for tall buildings. Let's come back to this one. Now we understand how loads happens. Now we are ready to explore what systems will make it happen nicely. Okay, so basically we have these basic ideas that we have walls and slabs resting on it. We have slabs and beams and columns, and we have subdivisions further, and then we have subdivisions either way. So these systems were common earlier, and they're still common, and the intent behind that was structural thinking. Okay, I have a span, I must get the maximum stiffness with least weight. That was the thinking, that I must get the maximum stiffness. Like you said, deflection should be reduced, was the primary thinking behind development of these systems. So people tried to, so they started with a thick slab, for example, and then try to remove as much material as you possibly can to keep the stiffness the same and reduce the weight. So this system here and here, they are here because you reduce the span of the slab further, the slab can be much thinner, and you retain the depth of the beam, so you have more ribs, but now the ribs can be narrower and so on. So you get the same stiffness or better stiffness than the slab with lesser weight and lesser concrete, because that was always the intent, to keep the stiffness, reduce the weight. And if you reduce the depth, the stiffness will reduce and you don't get a good response. So depth was always a criteria not to be changed, so that the stiffness will not be reduced, deflection will not be a problem, vibration will not. And engineers were able to convince architects and everybody that you have to do this one because other things were not known, right? But then gradually some engineer got smart and they say, oh, there are other ways to do these things. Okay, and then so we come to this one, flat slab, flat plate actually. They said, get rid of the beams. Let me design a flat plate and get rid of all the beams, which means all the material depth. Now I will just increase the slab thickness, like you said, enough to get the deflection right, but because now it's a two-way system, I can balance many things. This had a problem, flat plate. So this is the first idea, use flat plate. But when they started using flat plate, the problem was shear, punching shear, and deflection still could not be solved. Slab was becoming too thick. Span range was very small, maybe 6 meter, 5 meter, 6 meter, people could make it. After that, the slab became too thick, too heavy, not sustainable. Then you get the drop panel. They said, okay, if like this one, I have a punching shear problem and have deflection problem, why don't I put these drop panels and like column heads on top of the column? It will solve the problem of the punching shear, also reduce the span of the slab in between. So it became a very efficient way to just have the thickness over the column and reduce rest of the thickness. So flat plate converted to flat slab. Flat slab means have drop panels. And this was very popular at some point. Parking lots, everywhere people said, oh, this is great, I like it. Because longer spans were possible, still no beams are there in between, because the mechanical people can run their ducting here, they can put their stuff, and you don't. So there's a clear way to run all of the electrical mechanical system under the slab, and still the drop panel is there for structural. So it is very good compromise. From beams, people jump to this one, and so problem arise, they jump to this one. And then they say, okay, why don't we do this one, right? Waffle slab, very popular system for a while, because now you have very thin slab and very thin voids, and you can go much longer because your depth is large, weight is very less, and you have a distributed material everywhere, which all the material that you, so basically you have the effect of the slab thickness like this, but the weight of 1/3. So it was a very thick slab for very long spans, but take out all the weight. So then the waffle slab became, and still is, very popular for large span free space things. But the problem is form work. You know, it was difficult, a lot of fabrication, a lot of reinforcement stuff. And you know, in the beginning, in 80s, I used to use a lot of this in my projects. We used a lot of waffle slab. And there was a lot of contractors who made those forms from fiberglass had just come in. They started to make the fiberglass pans and reusable. So the contractor who had a formwork, they will get all the project because, Waffle slab became very popular. Hospital buildings, other places, very common, very popular. Heavy loads can be carried, libraries, because they're very stiff, very strong, still lightweight. Okay, 9, 10 meter, you can go, 12 meter, you can go with a Waffle slab. But now it's becoming out of date. It's in tall building, you don't do that anymore, okay? Because takes too long. Time is important. So flat plate and flat slab, and then you have this one. They said, okay, flat, this is interesting, but it's not good. It still takes up space. Why don't we just do this one, column capital? Just increase a little bit on the column and then get more depth here. And this becomes architecturally better. And then the head is reduced. So this became very, very popular, flat slab with column capital and drop panel and capital, right, in some cases. So all these systems are developed from the same idea: use the least amount of material where it is required, which is in the middle, increase it where the support is, where the punching shear is, where the shear is a problem, and then you keep getting all these variations of flat plate, flat slab with capitals, without capitals, and drop panels, right? So drop panels, column capitals, and flat plate. These three became very popular, still are very popular systems. And beams are not in fashion anymore. And of course, the Waffle slab and the beam slab still exist, but becoming less popular. For low-rise building, they're still used. Tall buildings, not so much. One of the reasons is that tall building, the span between the core and the first column is very long, typically 12 meters, 10 to 12 meters. There's just one span. So you need a system which works there. And now this is a nice example where somebody tried to put all the systems in one plan and show you how it works in a tall building. There's a core here, there's a periphery. So these are the beams outside. So they say, okay, how you can put many systems. One-way ribs became very popular at some point because you need long span. So narrow beams before post-tensioning and all. So these were joists. Then steel girder are used sometimes with these concrete slab. Composite decks came in because steel is very good as a beam. So you put the beam, light beam, narrow beam, not so deep, slab together also works. Okay. So this is just showing you how different variations can work. This spacing between the ribs is important. You can increase it to be a beam or reduce it to be a waffle. Here, only 20 to 30 inch, 600 millimeter, 900 millimeter, and go up to 2 meters. So you can vary. So this is where you're talking about optimization. You can find the best spacing of the rib and the depth of the rib and the size of the rib. And a lot of people did a lot of research to find the best combination of rib size, depth, thickness, slope, top slab, right? Because you can optimize it. And once you optimize it for one floor, you repeat it 100 times or 50 times. So it becomes very efficient. So a lot of work has been done on finding the optimum size of joists, spacing, type, and so on, whether concrete or steel. So this is a common structural system in many places still, especially in US, which they did not use post-tension so much. But now, even there, because they rely on steel. So they replace the joist with steel girders. The important one that when you start doing the design, and we'll discuss this later in after midterm, how to do the analysis and design. But when you start to doing the design using finite element, first time when ETABS put finite element or SAFE put finite element, the first problem was, what do I do with all these moments which are varying at all locations? Look at the plot. The moment color is varying at every location. So how do I calculate reinforcement? Which reinforcement should I provide? Because moment is varying at every location. I cannot change reinforcement on every location. It's impossible, right? So that means because the moment is changing on every location on the slab, how do I design the reinforcement? Which moment should I take? Which moment should I take? Yeah, that's the funny thing, maximum. Nobody cares about maximum because that's so inefficient, because that is only present at a very small location. This red dot is a maximum. So are you saying that you will take the maximum reinforcement, provide everywhere? It will be silly. People will not like it. So this idea of this engineer's concept, oh, I will take the maximum, is safe, doesn't work. This thinking doesn't work. So this idea that I should take the final, and people did that in the beginning, and they end up with so much reinforcement, nobody liked it. It's okay, let's go back to the old method, because people didn't use it correctly, right? And then, of course, research came and people come up with more ideas. We will talk more about this one, but we know we never use the maximum moment like that. So what do we do now? What do we use now? The idea, so look at this one. So if you go to SAP, if you go to ETABS and analyze slab, you will find contours changing everywhere, right? But the reinforcement, and there's a debate at this point how to handle it. And people are going, many ways. We are also working on it, how to convert the finite element analysis into a reasonable, practical rebar layout. But summary is something called design strip. And I will come back to this one. We use the concept of design strip to find a width of a slab and do the averaging of the moment based on some people like Wood Armor, two guys who did some research, and they found some interesting things, and we will discuss about that. And this, okay, this is how you should design the slab when you come from a finite element, because nobody knew how to do that, because finite element, you get 3 moments at every location, not one. You get M11, you get M1, M22, you got M13. 3 moments at every location. So which one you should pick? Because the direction of the moment is changing on every location of the slab, right? So we will discuss that, but the engineers have come up with the idea of the design strip, and now it is again going out of fashion because people think, oh, we have done such sophisticated finite element analysis only to simplify it by using an old method of design strip. This is not good. We should do a better job. Okay, so we are in the next level of iteration where we want to determine reinforcement directly from finite element analysis, still make it practical. Okay? And I will talk about that also. This could be a good thesis, actually. Okay, so we'll talk about. So after you have the concept of a design strip, basically this is the moment distribution, actual one, but you draw strips on it. One portion we call column strip, another one we call middle strip. And then we determine the reinforcement separately for column strip, bending moment in the column strip, bending moment in the middle strip, bands of reinforcement, because we see, oh, this pattern is different from this pattern. So this portion has a different reinforcement, and this portion has a different reinforcement. And it is determined on the concept of design strip. It is similar to what people used to do, slab reinforcement, different, transfer to beam. So now we think of these strips as support strips, and these strips as supported strips. So column strips, middle strips. And there's a whole rule and logic on their size and everything. We'll talk about that when we come to the design. But that's where we are moving to. Okay, so system application, we mentioned that you can use the system in many ways, and I can want to get back to this one, start from this again. So let's go back to that, because that is the basis for what we are going to discuss later. So first of all, important thing is that if you do a shell analysis on ETABS or in SAFE or SAP or whatever program, you will find something like this, that there will be a very large moment concentration over the columns, and then the moments will vary a lot rapidly. And in everywhere, so this is moments in one direction, this is called M11. So M11 means that the moment about one along one. So there are two, you already know the notation, and there is M11 and there is M22. Any two directions, arbitrary, not XY, in whichever is the local axis of the shell element. So it's based on that. And there is going to be then third moment is going to be M12, which is torsion. So we are always going to have 3 bending moments in the slab system, no matter how we do that. So M11, one direction, M22, second direction, and M12, the torsion. So depending on the supports, do not have to align with M11 and M22, because the M11, they are the local axis of the shell element. So if you mesh them like this, and the support is like this, and the bending is another direction, so the 2 moments have actually no meaning in terms of short direction, long direction, one way, two-way or anything. They are just two moments about two. So if this is the element, shell element like this one, these are the two x's, and this is the axis number 3. So this is 1, this is 2, this is number 3. So then one moment like this and one moment like this, there's going to be M22 and M11, and then 1-2 moment will be somewhere like this one in between. So that is the 3 moments going to be. So now when you have these 3 moments existing all the time, so now you imagine this, that there is a support, there's a slab like this, and if your element is like this, then M11 and M22 may be equal to Mx. This is, let's say, X direction, and this is Y direction. So then M1, let's say 11 and M22, M11 may become Mx and M22 may become My. But if the same slab, but your element, you meshed it like this, then the moment will be one will be here, 2 will be here, and 3 will be here. And they have nothing to do with the primary bending direction of the slab and Mx and My. So you cannot say this is the moment about short axis, this is the moment about long axis, this is the moment about X, about Y. They have nothing to do with that. The components of the moments, however, can be resolved in any direction because it's a vectors. So you can resolve the three moments back onto X or Y and do whatever you want to do with that. And this is the way that we proceed in the analysis and design. So this is if you go to the E-tabs, you will see that you can plot the moments, many moments and forces like that. We'll come back to that later. Let me go forward now to your question. Now watch carefully, please. And this time, I hope you all get what I'm trying to say. Let's say this is a one-way slab. That means these are the walls, and there is a P point load over there. One square feet or 1 square meter load is there called P. Half of that will go here, half of that will go here. So total moment load carried in X direction, which is this direction, is 1.0 P, and in Y direction is 0 P, correct? This is one-way behavior. So this is the definition of one-way behavior, that all 100% of the load will transfer in one direction, direct to the support, to the foundation, end of story. Okay, so that's it. Second case is now a two-way square slab in which there are beams here and there are columns, there are no walls here. Now, if you look at that, now the load will going to go, in this case, 0.25 this direction, 0.25 here, 0.25 here, 0.25 here. And then this 0.25 will go in this direction, this 0.25 will go in this direction. If you add them all up again in X and Y direction, you will find that you have 1.0 P total going in X direction, 1.0 P total going in Y direction. That means same P is fully being carried in X direction and fully being carried in Y direction. There is no shortcut around that. So which means that now you have this load 0.25, 0.25 plus 0.25 plus 2.5 in Y direction 1, and 0.25, 0.25, 0.25, 0.25 in X direction also 1. Now let's come to the slab which is not square. Now the load carried in each from the slab going to this side will not be equal. In this direction will maybe a little bit more, shorter span, 0.35, 0.35, 0.15, 0.15. Then 0.15, 0.15, 0.3. Once again, when you add them together, again, it will be 1 P in X direction, 1 P in Y direction. So this total equilibrium of the force transfer in a two-way will always be like that, irrespective of the size of the panel, irrespective of the long, short sides. Yes, for the slab, bending will be different, but the total load carried by slab and beams together in each direction will always be P and P. So this point, many people did not understand. They thought, oh, flat slab is unreasonable because it is carrying the same load in two directions, but because they think about only slab carrying to the beams, but they're not thinking about the beams carrying the same load again, right? So they thought that this is more efficient because this slab is only carrying like this one in this direction, and half of that, or half of that, half here. But they're not thinking that the beams are again carrying it again back to the column. So the total load carried is always the same. So now you're clear? So this is very important for the future, the next level of thinking, because which means that whether we have the beam or we don't have the beam, it won't matter. The load carried in X direction and Y direction will always be total load. It's just that part of that will go to beam, and part of that will go to slab. And if there is no beam, all will go to slab, and so on. So this is the basis for now. Let's say if we don't have any beam, then this half load will go this way, this half load will go this way, half load that way, half load that way, right? And in this one, same thing. It doesn't matter now, because there is no other way for the load to go anywhere, right? So this is the key understanding that we should have, that for a two-way system, no matter what, whether you use flat plate, flat slab, beam slab, waffle slab, it doesn't matter. Geometry is just physically the load for equilibrium, it has to go like that. Now it's just a matter of question, how do we distribute it back into columns and beams and slabs and the support columns, whatever not. So that is the next question. This was only realized very late, in maybe 70s, 60s. Before 60s, it was not like this. And British code followed much later. So ACI was the first one to recognize that. And then they thought, okay, in each direction, if that is the case, in each direction, if the load, full load is being carried, then we can simply divide the load or the slab into a design strip that we can take the building and say, okay, this portion, all of it is carrying this way, and similar strip will carry the load in that direction. So now we can independently split the slab into two direction wide beams or panels that will just carry the load in which direction. So one time they're carrying the load in this direction, one time they're carrying a load in that direction. And all of the load will be carried in X, and all of the load will be carried in Y. And that will help us to determine the bending moments from there on. So this was very clear, and this is very clear from the finite element analysis also, that if you, this is which is what is called, so this is one design strip from between, this is a column, you start in the middle of the column and the other middle of the column, next is just repeating the same pattern. So you take one portion away, which is the center of this column and center of this column, and you say, this is my strip, and I will take all the load on this strip and use it like a beam, because it's going to carry the load as in that direction fully. So now the other direction load carrying doesn't affect it. So I can just analyze that strip as a one-way beam resting on columns with a very wide beam. It's just a very wide flat beam, and then I'm just putting it on the column and I can calculate the bending moment. This was a great idea. And similarly, I can do the same thing. So we can bring that into just these strips, whether those beams exist or not. So we have kind of a virtual beams always present with that width that may have a real beam or may not have a real beam. It doesn't matter. And this was the key observation. And we will come back to this when we come to the analysis again. So this is what we have a panel, design strip, column strip, middle strip, drop panel. This terminology was then introduced to understand and design all of the system consistently. Please don't worry, we will go back to this analysis. Like right now, I'm just explaining to you the behavior. I'm not talking about the actual analysis for now. So then we say column capital, torsional members, equivalent frame. We will deal with all of these things one more time when we start the analysis part of this system. And then we'll come how to select the column strip, all of that, we will talk about that. I'm just giving you an overview. So basically what will happen is that we will take the slab and we will say, okay, this is my L2, this is my L1. L1 is along the length and L2 is perpendicular to the length. From that, I can split it into three types of strip: interior strip, exterior strip plus cantilever, or an exterior strip without cantilever. So those are the strips that you can think of in the building. So in a building, you will identify these three types of strips. You can also identify a top level strip, an intermediate strip, and so on, so that you have an intermediate strip, a general floor, and a top floor. These images are from Gear program 25 years ago, that we developed this flat slab or this slab design system using this concept without finite element, because this does not require finite element analysis, just requires a simple frame analysis or beam analysis, because the whole slab is converted into a one-way beam, wide beam, right? And we'll come back to that for the actual analysis, just give you an idea. So basically, you take the slab and you say, and right now in ETABS, we do the same thing. In SAP, we do the same thing. For practical design, we draw these strips And this is the design strip, this from here to here. And part of the purple is a column strip. It's like a beam, white beam on the columns carrying the load. This is the middle strip, two middle strip in this direction. And also in the same direction, we will do that. And this is the definition of those strips. After you do that, so the building is split into floor is split into design strips, and then you design the whole system based on this very simple but mathematically correct system. Okay. And then you take that strip, you calculate the total moment on that, and then you calculate negative moment, positive moment, because it's a one-way thing in this direction. Now, forget about the other side. That we will deal independently, because we already established that the two directions are independent. Each direction will carry 100% of the load. So we don't need to worry about the other direction when we are doing in one direction. We finish X direction, we go to Y direction and do the same thing again. And we calculate the reinforcement along this direction once, and then we reinforcement along the other direction second time. No interrelation, no overlap, no confusion about that. They don't affect each other at all. Okay, that's the important thing. So we calculate, and then from that you calculate the top negative reinforcement, positive reinforcement, and then you calculate that, and then you distribute between column strip and middle strip and beam and something, and we're done. So this concept is so simple. It just simplified the entire two-way slab system into a very, very conceptually clean and simplified method. Take like a beam, put the total load on it, calculate the bending moment, divide that moment into column strip and middle strip. From column strip, if there's a beam, put part of the moment in the beam based on the stiffness, because we already established that the load carried by a beam is based on its stiffness, not the geometry. So if the beam is very stiff, it will attract a lot of moment from the column strip. If it is not, it will not take any load. All of this moment will stay in the slab. So the distribution between slab and beam depends on the stiffness, and it's so simple now. So use the same system for beam slab, flat plate, Waffle slab, it doesn't matter. Okay, so that's the whole idea, and that's how this method. So whether it is a flat slab with drop panels, flat plate, ribbed slab, Waffle slab, flat plate, whatever, I put 5 systems on this one. I do run the analysis using the same strip concept. It works for all the systems. So you don't need to have 5, 6 different ways of designing these systems. There's only one way to design it, one way to analyze it, one way to handle it. The only difference is distribution of the moment between slab and beam, which depends on its stiffness ratio, and the column strip and width and the middle strip width depends on the span length. Those are the few rules there. Nothing more complicated than that. So based on that, then everything is simplified, and you can see I can get all the moments. I just put the design strips and I get all the moment, middle strip moment, column strip moment, middle strip moment, column strip moment. I got all the moments for all the systems in exactly the same matter. It doesn't matter that I have so many different systems there. It just worked consistently, right? And this is a great advantage because you don't need to learn so many systems to design. And then you get the column strip. So this is the column strip moment. This is the middle strip moment. You calculate reinforcement based on the middle strip moments. You calculate reinforcement based on the column strip moment. You distribute them based on that. And if there's a beam here, column strip moment in the slab will go down. You will have less reinforcement over the column, more reinforcement in the beam. If there's no beam there, more reinforcement in the column strip, and then you will have bands of reinforcement there. If there's a beam, no reinforcement there or very little reinforcement there. So you go back to the two-way slab concept where more reinforcement in the middle, less on the column. If there is no beam, more reinforcement on the column, less in the middle. So the entire transition between a flat slab system and a pure beam slab system is now consistently uniform. All right. So this is the key observation that you should know from the behavior and the analysis, and that's how we are doing it. So this is the column strip moment, middle strip. So you can see different systems. They will just the value in the moments may be different. This is with the drop panel. When you have a drop panel, more negative moment is attracted because more stiffness there. So you can see now that there is no drop panel. This moment is small. If you put a drop panel, because more stiffness at that location, more negative moment gets subtracted, positive moment gets reduced. That's the advantage, right? So we started with this stiffness-based moment attraction, and now we can see that it works all the way. This is flat plate. This is flat plate waffle slab. So waffle slab has, better. So you can just see that it doesn't really matter what system are you using. You just calculate the moments in the same way. This is for the rib slab. This is for the flat plate with column capitals. So every system gives you the moment. It just is different, slightly different, depending upon the size of the beam and column capital, no capital. But the analysis procedure, the design procedure is exactly the same. In fact, it's the same for reinforced concrete and post-tension. There is also no difference. You just put post-tensioning in those strips and you're done. Because post-tensioning is nothing more than a load, reverse load. So post-tensioning, I'll talk about in a minute, is nothing more than a reverse load that you applied on the slab to lift up the slab load in a negative direction. You subtract that load and you're done. So it's as simple as that. In concept, of course. In practical, of course, we still have to do many calculations. Okay? But concept is very clean. Okay, so now basically what we do is that we take the building. This is now the practical application. That's how you will do it, your project. You take the building, you take one floor, you can split it into frames if you don't want to use the ETABS directly, and you can use frame analysis here. And that's what we did in gear. We said, okay, we don't have finite element at that point. We take the building, we do frame by frame, one frame at a time, and one floor at a time. That's it. That's how the original method, and that's before the computers. When I started first time, you have to do the whole thing by hand. Imagine no computer even for frame analysis. So you have to take the slab out, you have to create these strips, and you have to calculate the bending moments in every location by hand. You have to distribute everything by hand, calculate the reinforcement by hand. It's a lot of work. There was nothing, no tools available, but the method was the same, right? So now you are very lucky. You take 2 minutes and you're done. Same thing would have taken me 1 week, right? And still we are not doing a better design. That's the sad part. We used to do better design, I'm quite sure, without computers. Anyway, so this is the concept. Now let's look at some interesting observation from the stiffness-based load distribution, taking it all the way. So I took a slab and I removed the beams here. So it's a mixed system. We have part of the slab is flat slab with no beams. Part of the slab is I put the beams there. Once again, same method applies whether you have all the system in one way or you have a mixed system. It doesn't really matter because strip is still a strip. So each bending moment here, so when you calculate the bending moment here, there is no beam, so all the moment will be carried by the slab. Here, part of the moment will be carried by the beam, part by slab, but it doesn't matter. Strip is still the strip. You will do the same concept. So there's no change. So I'm giving you an example where mixed systems can be handled exactly the same way. So you get this, you can see here, the moment now where the beam is, the moment is different. Where there's no beam, the red moment is different. Because now there's no beam, so no negative moment in the slab developed over there. It's only positive moment. So looking at this, you can immediately see how the system is behaving and how the moments are being distributed differently just from the colors. And from that, when you draw the strips over there, whether there's a beam or not, doesn't really matter. You get the bending moments and you will see that you get different bending moments at different locations. And then you can see the moment variation from that. And then you can plot the actual reverses provided. You can plot the reinforcement. You can see now the cage final reinforcement pattern is different because ETABS can also do the design and detailing. So when you look at the final reinforcement distribution, then you will see that there's more reinforcement here at the column top because there's no beam, less here. Look at the distribution here. This is more like a beam. There's less reinforcement close to the beam. There is more reinforcement in this area where there's no beam. So you can visually see the whole thing translating all the way to the rebar layout, right? So consistently, you start with the same approach. You do the finite element analysis. You can integrate the moments over a strip. So we take the average moment now, not the maximum. So I keep telling people, like you said, we take the maximum. We never take the maximum moment. We take the average moment over the strip, total moment over the strip. and divide it by the width. So you get the average moment. We design for average moment, not for the peak moment. And then we do all of that and you get the reinforcement patterns there. Okay, post-tension slab. Post-tension slab is no different from the ordinary slab. The only thing we have done now is that we have added these artificial beams. I shouldn't say artificial. We have added these physical tendons inside the slab. Normally we do it like this. So normally we post-tension the slabs using a bended and a uniform concept. In one direction, we put bended reinforcement, bended tendons like beams. And in one direction, we convert a two-way slab system into a one-way slab system now. Because you cannot have a good, realistic post-tensioning in two direction. It will disturb the system. We want to carry the loads in a very well-mannered structure. So normally, the two-way slabs are converted into kind of a one-way system for post-tensioning purposes. So this direction, these bands are called bands. So these are closely spaced tendons. They are supposed to be now the supports, like a beam, hidden beam. And in the other direction, we just put them. This is for simplicity of construction and also for the behavior. So we transfer this load here, and this load is then transferred to the column, same way as before. But now these tendons will help us to reverse the loading cleanly, because each tendon will actually, when you stress it, it has a profile, it will push the slab upwards. So it will balance the dead load. Normally, we balance about 80%, 80 to 90% of the dead load, and live load will still cause some bending moment, for which we provide reinforcement. So that's how it will work. So you can see from here that this is the profile of the tendon inside the slab, exaggerated, of course, on the height. So you can put the profile like this. Typically, you control that, and based on this profile, when you stretch it, this tendon tries to straighten up, and in process, it lifts the slab up and then carries the load upward. So it's just a load balancing system. So basically, post-tensioning has two effects. One is that it balances the load, and second effect is that it compresses the slab with compression, reducing the tension. So it has a double effect, not single. So if the tendon is straight, it has only one effect. Putting compression in the slab and reversing the tension, that's okay, but that's not going to be enough. You need a lot of post-tensioning to put enough compression. So we do two things at the same time. We lift up the slab. At the same time, we post-tension and reduce the tension at the same time, okay, and add compression. So now the challenge is that this post-tensioning should be done in such a way that you don't overlift the slab. If you overlift the slab, tension will develop at the top and everything will break and crack. Because if you provide over post-tensioning and you push it, and the dead load is not there to balance it, slab will lift upwards and crack and break. And it has happened. So post-tensioning is to be designed in a very sweet spot, not too much that it causes uplift to cause tension at the top, not so little that it causes tension at the bottom from the load. So it has to be just perfect. And that is a very, very hard thing to do because slabs are complicated and the profiles cannot be perfectly managed. So it's even if you try very hard, in the end, some tension is likely to develop. So we try to keep it in a certain manner. So stresses need to be checked. You also need to add some reinforcement for accidental tension being developed, and also to take care of the tension developed by loads that you could not balance, like moving load or live load. So this is the basic concept that they will be teaching you, and then you will use that. So in the end, the 3D tendon profile will look something like these are the end something, and then this is, you can see like that. So this is the tendon profile. This is all, by the way, developed here. This whole detailer, this whole post-tensioning system, you know, all of the things that you see here. So then you put that, and then you analyze it, and then you combine it with the bending moments from the other live load cases. You get near zero, well, not really, but almost close to zero moment everywhere, or should be ideally close to zero because the slab is perfectly straight, no deflections. So the problem of the deflection by thin slab is now solved by post-tensioning. So you can further reduce the slab thickness, because if you did not use that, deflection will be very large. You'll have to increase the slab thickness, which will add weight, which will increase deflection and so on. So post-tensioning is a way to break that deflection cycle and then reduce the deflections and vibrations also to some extent. So that's how it will be, this moments due to gravity load and moments due to post-tensioning. So we basically reverse, this is the moment downwards, and post-tensioning will put the moment upward. So we get completely reversed bending moment profile from dead load and post-tensioning. And we try to make them such a way that when you add them together, they will be nearly close to zero. So that's the magic of post-tensioning. That's why almost all tall buildings now use invariably post-tension flat slabs, because they are easy, they are flat, they are easy to construct, they don't have a deflection, and so on. And then you can have longer spans up to 9-10 meter is possible without beam. So this is around from here to there. You can have a slab, post-tension slab running that way. So it's pretty large, long span. So gravity and you can see the reverse moments completely reversed. And so reinforcement is still required for, this is reinforced and this is post-tension. The reinforcement required now, as you can see, is much less. You only require reinforcement for accidental tension and for live load, not for dead load anymore. So the reinforcement required is still required, but is much less than the one without the post-tensioning. So you can see from here, this is post-tension. Also, almost no reinforcement required in this region, almost. And here you can see so much reinforcement required. Of course, this is by computation, but minimum reinforcement may still be provided. A mesh may be still provided. This is for the top bars. Now you can see in post-tension, top bars may be more required because, like I said, you have over, in this particular case, I didn't balance things exactly, so there's more upward moment. This is not a perfect design. I just, it's a template sort of thing. So you have to optimize it, go back, change the post-tensioning force, change the ordinate of the things, and then balance it better. This is just, just quick design. Okay, so that's the bending problem in the slab and the two-way action and the post-tensioning and the way that we distribute. One more important thing that we need to also consider is the shear in slabs, in flat slab, and that is the punching shear. So this is the one-way shear, and this is the punching shear. So what we are most worried about is the punching shear in flat slab, because the slab can break around the column and fall down. And this is the most common failure type in slab system that have occurred so many times. And I told you the story about my slab, right? Okay, sad story, but yes. So look at this picture that you see here, this one here. So in 1984, 85, I designed my flat plate system. I was very fond of the flat slab system, so I designed. And then one day morning, I was sleeping at, I think 5 a.m. or 6 a.m. Somebody knocked my door at my home and he said, the slab that you designed has fallen down like that. It has collapsed 4 floors. They're all collapsed down. So you cannot imagine the feeling that you have when your structure has collapsed and then people are knocking at your door and asking you to go to the site. So of course I rushed. I called my friend, another one that, and luckily nobody got hurt. It happened at night when there's nobody at the site. So lucky for me and lucky for everyone that nobody got hurt. But the whole structure, actually 4-story, collapsed like that. It was like, it just fell down and it collapsed like a pancake. And the columns are still standing. So obviously, and it's all done by hand and everything. So my first question, everybody's design is okay or not. So I went back, checked my calculation. Everything is okay. I asked my friend. He also checked my calculation. He said, there's no error in the calculation. I also went to the site in the big 1 or 2 times. I know the slab thickness was okay. So there is not a site construction problem also. Then what happened? And then we learned some interesting thing that they were going to cast the 4th slab, 4th floor, and this is what they did. And this is something for you to remember always. And actually, after that slab that collapsed in my project and many other collapses, I will tell you what the codes did after that. So watch this carefully. So what happened in my project was that this is this slab. This is one slab. This is another slab, columns here, another slab, and foundations. So they're going to cast this slab. So they put the formwork, all of that formwork on the slab below that. And then also they stored the material like cement bags and something to mix the concrete, because mixing is done by hand. There is no delivery of concrete at that time. So they said, okay, we don't need to put the concrete here. Why don't we mix here and then we can take it? And they put all of the concrete mixing and the material plus the weight of this slab on top of this slab, and they did not brace this further. So this slab basically carried about 3 times the design load that was designed for. Of course, there is no 3 times margin in that one. So this slab at this point actually, it had a punching shear failure. So this fell down, that fell down on this one, this fell down on that one, and then everything fell down. Okay. So the important point is that when you do the casting of these slabs, you must support the slab below all the way. And that was the instruction. But the contractor wanted to, save that supports, and they just move it there. So it's a construction. Most of the failures happen in construction. You have seen how many failures are happening in construction these days, unfortunately, in Thailand. So many have happened, so many people. Construction is the most difficult, serious time of construction. A lot of the failures happen during construction. Construction overloads, construction process not being followed, construction rules not being followed. And this was one of those cases where the contractor did not follow the rules, and they actually put 3 to 4 times more load on the slab than they were supposed to be. So then this happened not only in my project, all over the world, this was happening, right? And if you see now punching shear failure, you will find hundreds of pictures. So the codes start to get, to realize that this is not good. So now what they've done is, in the most recent codes, recent means 10, 15 years ago, they ask you to put bottom reinforcement here at the bottom in such a way that it can, if it fails down, the whole slab can hang from the columns. So there is a extra reinforcement to be put on the bottom of the column, not on the top, because top breaks. The bottom of the which is not required by analysis. You don't need bottom reinforcement over column because moment is negative. So nobody provides any reinforcement at the bottom on the column. They said, no, you must provide very large diameter, 3 or 4 bars at the top of the column, enough to carry the whole slab if it fails by hanging, so it doesn't fall down. So now that is part of the design requirement, that you should provide enough reinforcement at the bottom of the slab on each column in each direction to carry the entire weight of the slab by hanging, so it doesn't fall down. It may break, but it should still not fall down and crash the slab below that. So anyway, so this is so important. So having punching shear prevention is very important. So and punching shear becomes very complicated, not because of the punching shear, but mostly because of the moment transfer causes the punching stress to vary and exceed, not the normal one. Because the bending moment, you have additional stresses developing around the column, and that causes this stress to exceed on one side and it break from there. Normally it's the corner column and the edge column which start the failure. Okay, so this is the prevention of the large failure. Provide large diameter bars at the bottom of the column, provide proper reshoring. Most failure occur during construction, everything like mentioned to you. Okay, so these are the basic rules we must follow when we do flat slab construction. Mostly provide column capitals or drop panels to prevent this from happening. So flat plate is not a good thing, but sometimes we have to do it because it's fast. So people also provide steel studs, steel reinforcement, steel section on the column to prevent this from happening. So there's a lot of things being done now, but wasn't there earlier when the system was being developed. So this kind of thing, the shear studs are placed, this kind of things are being placed. So people are really taking a lot of care that the slab should not fail at the top of the column. So this is quite a, this shear stud arrangement is now common, people are doing that. And those bottom, look at those bottom big, large diameter bars. See this? This is what I'm talking about. These bars are designed to hang the whole slab if it collapses. On top of that, there's another prevention through steel frame inside. Okay. So shear studs like that, or steel plate studs plus bottom bars, because people just don't want this to happen anymore. It is so serious. Of course, it's very serious. So that's the thing. So you need to prevent the top bars do not help. So bottom bars are designed to carry the hanging slab now.